Now, let me summarize different interpolation in beam formulation. So, for one beam element has two node coordinate x 1 and x 2, associated dependent variable at each node are deflection and rotation. So, for one element, elemental vector for dependent variable deflection is downward positive, rotation is clockwise positive. For coordinate, we have usual Lagrange interpolation, whereas for dependent variable we have Hermite shape function, already these nodal values of dependent variable we have defined. This n is we have the expression for n1 n2 then d2w dx2 is in this form, where B is again 1 cross 4, 4 cross 1, where B is for variation the same expression only with nodal values of variation. Now, we revisit the variational statement. Here, as I mentioned earlier, boundary terms will be taken care at the global level So, the remaining variational statement can be written as in this form. This is for a particular element. Now, we can substitute the interpolation relations. Dx is Le by 2 dxi. We are transforming to parametric space. So, limit is -1 to 1. Now, d2w dx2 is b w e hat, and because our final term is a scalar quantity, we have used transpose, which essentially tells us that B is 1 cross 4, W E hat is 4 cross 1, B transpose is 4 cross 1, this is 1 cross 4. So, finally, it will give us 1 cross 1. Let us first understand this element stiffness matrix. So, we can take this V E hat transpose outside, E I L E by 2, B transpose B dxi we can take V transpose and W E hat outside as they are not function of xi. Now, we assume for one element Young modulus and moment of inertia are constant throughout the element. So, this is the element stiffness matrix. So, element stiffness matrix is E I L E by 2 So, you remember here this B is function of xi. So, finally, it will be a 4 cross 4 matrix. Now, if you perform this integration for each of the 16 element of the matrix, you will finally get Ke equal to this form. This integration is done symbolically to get the symbolic form directly. Now, I will explain in this element stiffness matrix one term explicitly to understand how this is coming. So, our Ke is Ei Le by 2 minus 1 to 1 B transpose B dxi. So, I am explaining this second row fourth column term. So, Ei Le by 2 minus 1 to 1. Now, if you see the expression of B, then there will be 4 by Le square. So, that will be 16 by Le to the power 4. Now, B transpose 3 xi by 2 Le by 4 3 xi minus 1 minus 3 xi by 2 Le by 4 3 xi plus 1 . For B already 4 by Le square I have taken care here. So, Le by 4 3 xi minus 1 minus 3 xi by 2, then the fourth term Le by 4 3 xi plus 1. Then this is dxi. Now, I want to understand this 2 comma 4. So, this is your 4 cross 1 and 1 cross 4 will give 4 cross 4. Now, to get this 2 comma 4, so Ke 2 comma 4 will be Ei Le by 2 16 Le to the power 4, because it is second row. So, minus 1 to 1 Le by 4 3 xi minus 1. So, for getting 2 comma 4, that is in second row and fourth column. So, we have to take the second row term of the first B transpose and fourth column term of B dxi. Now, if you see this 16 will be cancelled by this 4 and 4, then there are 3 Le, altogether there will be 1 Le in denominator. So, it will be Ei by 2 Le. Now, inside integration we have 3 xi minus 1, 3 xi plus 1, that is 9 xi square minus 1. So, E I by 2 LE, this will be 9 by 3 xi cube. So, 2 minus 2. Leap, that will be 18 minus 6 by 3, that will be 12, that is 4. So, 4 E I by 2 L E. Now, there is a common factor in all 16 term E I by L E cube. So, it will be multiplied with 2 L E square. So, you can see I have obtained this 2 L E square. Here E I by L E cube is common for all 16 term. Thus, we have understood how to get the term of this element stiffness matrix for beam formulation. Now, we have derived the elemental stiffness matrix. So, if we see our variational statement, now we will see how to get the elemental load vector for beam problem. So, in variational statement, this is your load vector part for distributed load Q. Variation V can be written as and dx LE by 2 d xi. Now, the limit should be minus 1 to 1. Now, this is not function of xi. So, finally, we have this is our element load vector Fe. Where this n vector, if you see, so this is our n vector which are function of xi. So, if you do the integration, then for uniform distributed load Q, this will be Q LE by 2. After you do the integration symbolically, this is your element load vector for uniformly distributed load. So, in left hand side, this VE hat transpose appear. Similarly, in right hand side. Now, if you see the variational statement, then as I mentioned, boundary terms are taken care at the global level, and for this elemental equation finally we have here this VE hat transpose is not appearing considering the arbitrariness of variation. We explained this earlier. So, this is our final elemental equation where the element stiffness matrix is this matrix, and our element load vector for uniformly distributed load is this, and WE is this 4 cross 1 vector considering deflection and rotation at 2 end nodes. Now, we will solve 2 examples using this beam formulation. This is our first example where both boundary has simply supported, that is deflection is 0 and they are free to rotate, there is no end moment. Now, if you see, there is one concentrated load at this point, there is one moment at this point, and there is distributed load which is uniform in the section L2. First, we have to discretize the domain. We require one node at this point of F. Also, we require one node at the point where moment is acting. We have to take nodes at these 2 points. Let us discretize the domain into different elements. So, here F is acting, here moment is acting. We have to consider a node at this point. Node 2, node 3, node 4 and node 5. This is our element 1, element 2, element 3, element 4. This whole length L2 should be considered in a separate element because only that portion is subjected to distributed load, which is element 2. Considering all these factors, the entire domain we require minimum 4 elements. Now, this is our origin. So, if we write our coordinates for the entire domain, for node 1 0, 2, for node 3 it is 4, So, L1 is 2, L2 is 2, L3 is 1 and L4 is 1. So, at node 4 it is 5 and at node 5 it is 6. And for this problem, boundary condition at x equal to 0, your deflection is 0 and your moment is 0, it is free to rotate, there is rotation. Similarly, at x equal to 6, we have the same boundary condition. We will explain implementation of beam formulation in Matlab through this example. Now, let us see the Matlab functions. First, this function is calculating element stiffness matrix, where the input is Young modulus E, area moment of inertia I and the nodal coordinate of that element. This is our element stiffness matrix. So, we have calculated that in this function and this Ke is the output of this function L is stiff. Now, if we see the main program, here for each element only thing which is changing, that is nodal coordinate for that element. So, for first element 0, 2, for second element if you see it is 2, 4. So, for second element 2 and 4, for third element 4, 5, 4, 5 and for fourth element 5, 6. So, only this is changing from element to element and we calculate element stiffness matrix K1 for element 1, K2 for element 2, K3 and K4 for element 3 and 4. If you do the calculation, this will be your K1. Now, as in truss element, for each node there are 2 degree of freedom. So, for ith node the global degree of freedom will be 2i minus 1 and 2i, that is for ith node your global degree of freedom. So, here with this formula, these are the associated global degree of freedom for element 1. So, 2i minus 1 is for deflection at ith node and 2i corresponding to rotation at ith node. So, here the nodes are 1 and 2 for first element. So, global degree of freedom 1, 2, 3, 4 for first element. So, we are marking each column and row with the associated global degree of freedom. Similarly, for element 2, associated global degree of freedom for node 2 is 3 and 4, that is 3 is corresponding to deflection at node 2, 4 is corresponding to rotation at node 2. Similarly, for node 3, 5 and 6. So, we mark the rows and columns as 3, 4, 5, 6. For element 3, global degree of freedom are 5, 6, 7, 8, and for element 4 they are 7, 8, 9, 10. Now, we have to do the assembly. So, we know in assembly the entries corresponding to same global degree of freedom row and column will be added. For example, here this 7 comma 7, that is this red square bracket term will be added to this entry 7 comma 7. So, these two will be added, and if you see the global stiffness matrix, that 7 comma 7 is the addition of that two term. So, again here for better understanding, I have marked each element term with same symbol, like 4 comma 4 is circled with blue circle, that is appearing in first element with this term, also in second element 4 comma 4 it is marked with blue circle. This is not appearing in any other element. So, if you add these two, that will be 4.2 into 10 to the power 5. You can see in our global stiffness matrix 4 comma 4 is with blue circle 4.2 to the power 5. Similarly, that holds for other entries also, like third row fourth column with red square. Similarly, third row fourth column with this. Now, if you add these two, that will be 0. So, in your global stiffness matrix third row fourth column is 0. So, you can see I explained few terms with different symbol, and the contributing element term are also with same symbol. In this way, we assemble these 4 element stiffness matrix into this global stiffness matrix. So, global degree of freedom there are 10. So, the size is 10 cross 10. Let us see how this assembly is done in Matlab. So, first I have assumed a 10 cross 10 0 matrix. Then the K1, that is, if you see for K1 the global DOF are 1 to 4. So, they are simply assigned. For K2 the global DOF is 3 to 6. So, these are the address where these elements of K2 will enter. So, 3 to 6 are the global address. So, if you see in the Matlab program, 3 to 6 is the address in the global K. Now, here we have added because this 3 4 already appeared in K1. So, this will be added with this. So, we have added with already existing entries. Similarly, for element 3 the global address are 5 to 8, and for element 4 global address are 7 to 10. You can see in the Matlab program K3 is added from 5th row to 8th row and 5th column to 8th column, and K4 is added to 7 to 10 row and 7 to 10 column. Thus, we have performed the assembly in Matlab. Now, in this example, only for this element 2 we have some uniformly distributed load, which has to be taken care at element level. So, this is your element load vector for uniform Q. Let us see in Matlab. So, in Matlab again this FE is the element load vector for that element, where we are giving that uniform load Q and the nodal coordinate for that element. In the main program, so only for element 2 we are calculating this element load vector F2. So, this will be your F2. So, associated global address is 3 to 6 corresponding to node 2 and node 3. For this problem, there are also this load point load F and moment M at node 2 and node 4. So, point load is associated with deflection degree of freedom. So, node 2, that point load will be acting at DOF 3. So, at third entry of global load vector, this point load will be directly added, and point moment that will be associated with rotation degree of freedom of the corresponding node. So, in this case for fourth node, the global degree of freedom associated with rotation is 8, that is coming from 2I, where I is the node number, which is 8. So, the 8th entry of global load vector, there will be this M which will be added to F8. So, also regarding sign, we know the loading point load is positive if it is downward, because our deflection convention is downward positive. So, in this case F is positive, which is 10,000 Newton, and also our moment is positive clockwise, because our rotation is convention is rotation is positive clockwise. So, here M is also positive. So, this will be positive 10,000 and our moment is 3000, that is also positive. So, if we write our F3, already we have some entry from uniform load contribution, that is 2000. So, 2000 plus 10,000. So, F3 will be 12,000, and there is no contribution from any other load in 8th DOF. So, F8 will be 3000. So, if we write our global load vector, third entry will be 12,000, fourth entry will be 666.667, So, this is global DOF 1, global DOF 2, 3, 4, 5, 6, 7, the 8th entry coming from point moment, that is 3000, and your 9 and 10 will be 0. So, there are 3 loading part. This uniformly distributed load is directly going to our global load vector in the respective address 3 to 6. Note 3, because of point load there is this additional F, and at note 8 there is this moment. So, this is our global load vector for this problem. Let us see in Matlab how this is implemented. So, for element 2 we get this F2 for uniformly distributed load. Now, the global address of F2 is 3 to 6, 3, 4, 5, 6. Then at the third node we have added this point load P, that is 10,000. It is positive because it is downward, and 8 degree of freedom, that is rotation degree of freedom corresponding to node 4, where point moment M is applied, which is 3000 Newton meter. And always be consistent with the unit. Throughout my lectures I am using SI unit. So, both P and M should be in SI unit. Thus, the global load vector is formed. So, this is your global equation. Now, we have to impose the boundary conditions. Here we have 2 boundary conditions. For node 1, deflection is 0, that is W1 is 0, and for node 5, that is the rightmost node, your deflection is 0. Now, for 5th node, deflection is corresponding to 2i minus 1, that is 9. So, W9 will be 0. So, these 2 boundary conditions are given. Other 2 boundary conditions, that is at left and right boundary nodes, moments are 0. These are natural boundary condition. These boundary conditions are directly taken care in the variational statement. If you see the variational statement again, so here at this part, that natural boundary condition is automatically taken care, that is 0. During imposition of boundary condition, only we have to consider essential boundary condition. Now, here W1 is 0 and W9 is 0. So, the first row and first column will be eliminated. So, we strike out first row and first column. Similarly, the 9th row and 9th column will be eliminated. And because these are 0 boundary condition, so our load vector remain unchanged. So, after imposing these 2 boundary condition, our unknown will be 8. These are our equation after imposing boundary condition, which is 8 cross 8. If we solve this in Matlab, we will get this 2 to 8 and this 10 after doing the inverse of that matrix, and then already given W1 and W9 I have added. Then if we do this further post processing, that is K, already that 10 cross 10 global stiffness matrix before imposition of boundary condition, this is that K. If we do that K Wn, where Wn is our total 10 cross 1 dependent variable vector at nodes, then we get this F, where corresponding to first degree of freedom and 9th degree of freedom, these are the reaction force at left boundary and right boundary. So, these are our reaction force. Now, let us see these steps in Matlab. So, after getting global K and global F at this step, then the reduced stiffness matrix is obtained. You can see I have taken from second row to 8th row and 10th row. So, we have eliminated first row and 9th row, similarly first column and 9th column. So, that is our reduced K and our reduced F. So, at this step we impose the boundary condition. After that, our Matlab inbuilt function inverse I have used to get the 8 cross 1, that is the unknown degree of freedom that we get by doing this K inverse F. After that, to this reduce U, that is we have from 2nd degree of freedom to 8th degree of freedom and the 10th degree of freedom. So, we insert the U1 and U9 which are 0, and finally we get this reaction force. Now, for this problem, this is the analytical solution, where this bracket means, so by x minus 2 we mean x minus 2 when x is greater than 2 and it is 0 when x is less than equal to 2. So, this is the meaning of this bracket. So, this is the analytical solution for this problem for this F, M and Q naught. Now, in Matlab we have coded that analytical solution, and finally if you do the plot for FEM solution and analytical solution. So, in this part we did the post processing, where we have found the FEM displacement at different points other than nodes. So, this is our U numerical, that is numerical displacement, and also we have coded the analytical solution in this portion. Now, if you do the plotting of these two, so you can see this blue graph is the analytical solution and these red dots are FEM result. So, you can see here FEM result is matching with analytical. So, if we revisit the Matlab program, we calculate element stiffness matrix K1, K2, K3, K4 and the element load vector F2. Then we do assembly of stiffness matrices and element load vectors. After that we take care point load and point moment at global level. Then we do the imposition of boundary condition at this step. After that we do post processing to get the reaction force, and finally we plot FEM result on the top of analytical solution, and we can see the exact match between finite element result and our analytical result.